All right, finishing up this unit, we have solution concentration. A reminder, a solution is a homogeneous mixture, has a uniform composition, particles are too small to tell apart from one another. Components can be separated through processes like distillation. That would be one example. All right, some terminology. The substance that is being dissolved is called the solute, and then the substance that is doing the dissolving is called the solvent. So for example, if you had salt water, the salt would be the solute, the water would be the solvent. In fact, when water is a solvent, we give it a special name. We call it an aqueous solution. Most of the solutions that we'll deal with in this class will be aqueous solutions. We've seen mass percentage before, has multiple contexts. So in this case, we're talking about the mass percentage or percent by mass of a solution. And so same setup as before to calculate mass percent. So in terms of a solution, again, for anything, it's part over whole. So it's the mass of one thing over the mass of the whole thing. So in the case of a solution, usually it's the mass of, and it could go either way. You can find percent by mass of the solute or percent by mass of the solvent. Usually it's the solute. So mass of the solute over the sum of the masses of the solvent and solute, or mass of the solution goes on the bottom. Take a look on page 100 at the examples. Let me walk you through 314. Read along, please. It says, calculate the mass of nickel 2 sulfate, NiSO4, contained in 200 grams of a 6.00% of nickel 2 sulfate. So we're going to use that percent like we have before as a conversion factor. And so we're going to start off with the mass of the solution, which is 200 grams. Make sure to label everything as always. So I use the abbreviation SOLN for solution. So the total mass of the solution, 200 grams, of which 6% of its mass comes from just the solute. So we'll set that up as a conversion factor. So 6 grams per 100 grams of solution. Grams of solution cancel, and we get our answer, which is 12.0 grams. So if you take a look at example 13.5, tells you how many grams of nickel 2 sulfate are in the solution. Same solution, 6%. This time trying to find the mass of the whole solution. So similar setup. You start off with the 40 grams of nickel 2 sulfate. Use the percentage composition as a conversion factor. This time it's going to be 100 grams of solution, since that's what we're trying to find, over 6 grams of the solute. All right, go to page 101. Take a look at example 13.7. Sorry, that would be 317 on page 101. So similar approach to 315 in that we're given the mass of the solute in some solution, 30 grams this time of iron 3 nitrate. And it gives us the percentage composition of that solution, 15% by mass of iron 3 nitrate. And then this time, though, we want to find the volume of the solution that would contain that much of the solute. So again, we're going to use percentage composition as a conversion factor, 100 grams of solution over 30.0 grams of the solutes. That'll give us the mass of the solution. And then the question asks for volume. If we're given mass, asked to find volume, use density. So we're given the density of the solution. We'll use that as a conversion factor as well. Sorry, I know the notes are a little bit out of order. I wanted to do 317 before you move on to your own practice. So take a look on page 112. Please do number 59. Pause the video. So check your setup. We're using density as a conversion factor. Given the volume of the solution, we can find the mass of the solution. And then we're going to use the percentage composition to convert from the mass of the solution to the mass of the solute. You should end up with 109 grams. All right, go ahead and pause and do number 61, also on page 112. So I have a green triangle for number 61. So a little bit more involved. We start off with the mass of the solute given to us in the problem, 70.6 grams. It says we want a 25% excess of this substance, so that's why I did that first conversion factor. So just 125% over 100%. So that's going to give us some amount, 125% of 70.6 grams. and then again apply our percentage composition and density to find the volume. So I've already seen one way of expressing the concentration of a solution, that is by percentage composition or percent by mass. There are other ways such as molarity, but the most common way of expressing the concentration of a solution is molarity. Let's write the formula. Symbol for molarity is big M, and it's a ratio, as are all solution concentrations. It's a ratio, the amount of solute per amount of solvent or solution. In this case, and don't just write this, make sure you know what those are. Moles of the solute per liter of the solution. If you go to page 102 in your textbooks, it explains how to make an aqueous solution using a volumetric flask. So anytime you want to prepare a solution of a specific concentration, you got to follow that method. We'll be making lots and lots and lots of solutions in this class. So please follow the procedure, especially when we get to the point where you're going to need to prepare a solution. You're going to refer back to that page in the book, and it goes through the steps for you. All right, let's take a look back on example 318. Read along, please. It says, calculate the molarity, or molar concentration, sometimes it'll say, of a solution that contains 3.65 grams of hydrogen chloride gas dissolved in 2.00 liters of solution. So we're given the mass of the solute, which is hydrogen chloride, 3.65 grams. And we need the amount of the solute in moles, so we're going to convert to moles. So I'm going to do this all in one shot. You could break it up into two steps, find the moles first, and then divide by the volume. I'm just going to do it all together. Take that, divide it by the volume of the solution. And that should get you your molarity. Go ahead and pause the video, calculate that, and compare with the book. Notice that the book sets it up a little bit different. That's fine. Sometimes we can use molarity as a conversion factor, but I like doing it this way. I got moles on top, liters in the bottom. We get molarity, which is 0.0500. I don't like how the book gives the answer. That's one way of expressing it, but instead of in moles per liter, let's just write that as molar anytime we're calculating the concentration of a solution. 0.0500 molar. All right, number 63 on page 112, very similar. Go ahead and set that up. Do it all in one shot if you can, and pause the video. So you should end up with 1.71 molar for the concentration. All right, go back to 102, take a look at 319. Little different problem, very common problem. Calculate the mass of barium hydroxide required to prepare 2.50 liters of a 0.0600 molar solution of barium hydroxide. So this time we are given the concentration and we're given the volume. Anytime you're given the concentration of a solution and the volume of a solution, we can use that to find moles. So take the molarity multiplied by the volume of the solution in liters. I've just taken that molarity equation, rearranged it, and we get moles of solute. Very common calculation because you need to know how much of this substance do I need to make this particular solution. And so you got to find that first in moles, and then once you know the moles of the substance, you can use the molar mass to find grams. And so that's what they show you in the book. Again, they show it a little bit different than what I have here, but essentially it's the same thing. Get moles, multiply that by a conversion factor, molar mass, and you get grams. All right, go ahead and pause the video. Work on 65B. There's two parts. Just do letter B. Pause and check your answer when you're done. So we want 3 sig figs in the answer. So there's no way to write 6,700 3 sig figs without putting in scientific notation. So I put it in scientific notation. All right, back to 103, 320. Little different problem. Read along, please. It says a sample of commercial sulfuric acid is 96.4% H2SO4 by mass. And it's, change that. I'm not going to use that word there. What does that mean? Its density is 1.84 grams per milliliter. All right, take a look at the solution. First thing we're going to do, we're going to use the percentage composition of that solution. We'll assume there's 100 grams of the solution. So in 100 grams of the solution, 96.4 grams of it is H2SO4. So we can use that along with the density to find the grams of H2SO4 in the solution, in 1 liter of solution. So we want liters, so we'll do it per liter. So we have 1.84 times 10 to the third grams of the solution. Actually, the book sets it up a little bit different. They find out the total mass of the solution per liter and then apply the percentage composition. You can apply the percentage composition first if you want. Main thing is we got to find grams of H2SO4, take that, convert it to moles, and then divide by 1 liter. So we end up with a really big value, 18.1 molar sulfuric acid. Concentrated sulfuric acid is really nasty stuff. All right, go ahead and work on exercise 71 on page 112. Please pause the video. And the main idea here is we want moles per liter. So we need liters in the bottom. So I took that density, converted it to grams per liter, that first conversion factor. Percentage composition to find grams of just the solutes. And then, again, that's going to be grams per liter. The liters doesn't cancel. So if you look at the units, milliliters cancels here. We have grams of solution cancels here. Grams of our solute cancels. And so what are we left with? We're left with moles of our solute per every 1 liter, aka molarity. Another very important skill besides knowing how to calculate the mass of a solute needed to make a solution is diluting solution. So sometimes you're given a stock solution, a solution that's already been prepared for you, and you need to dilute it. When a solution is diluted, remember that the amount of solute does not change, but the amount of solvent increases. And if you look at the formula for molarity, if the volume increases, then what happens to the concentration? Well, the concentration will decrease. Remember, it's a ratio. So mole stays the same. You're increasing the volume of the solution, thus the concentration will decrease. So a little derivation of the formula. Moles of solute before you dilute is the same as moles of solute after you dilute. Well, how do you know how many moles of solute are in a solution? You can take the molarity of that solution, multiply it by the volume in liters. By the way, if you multiply the concentration, the molar concentration of a solution by the volume in milliliters, you get something called millimoles, which is something that we'll deal with later in this class. So for now, we'll just deal with moles. So molarity times liters, volume in liters will give you moles. So let's substitute that. We have moles before you dilute is the same as moles after. So M times V before you dilute is equal to M times V after you dilute. And so this is the formula, or how I write it for dilution. So the ones represent the initial conditions, so the initial concentration and the initial volume. So that's before you dilute. And then the twos represent after diluting. Concentration after you dilute, M2. Volume after you dilute, V2. Remember, V2 has to be bigger than V1 if you're diluting. And if V2 is bigger than V1, then M2 has to be smaller than M1. You can also use this formula if you take a solution and evaporate some of the solvent from it. So in this case, if you heat up a solution and evaporate some of the solvents, the volume is going to decrease. And if the volume decreases, then the concentration will increase. Now, this only works when you heat up a solution that contains a non-volatile solute. Non-volatile means non-evaporating. So sodium chloride, for example, is a non-volatile solute. Ethanol would be an example of a volatile solute, and then this process would not work. If you heated up a solution of water and ethanol, both the water and the ethanol would evaporate, and I don't know which one would evaporate faster, probably the ethanol. And so who knows what happens with the concentration in that situation. Go to page 104. They show, again, how to dilute. You're taking a solution. To that solution, you're increasing its volume by adding more solvent, which in this case is water. And that causes the concentration to decrease. All right, 105, example 321. How many milliliters of 18.0 molar H2SO4 solution are required to prepare 1.00 liters of a 0.900 molar solution? So we apply our formula, M1 V1 equals M2 V2. We're solving for V2. Notice that the V1 is given to us in liters, but the question asks for the answer in milliliters. So if you want, you can convert V1 to milliliters. So that would be 1,000 milliliters. And then your answer would be in milliliters, which is 50.0. Again, a very, very, very common calculation that you will do in this class. All right, go ahead and pause the video. Work on number 73 on page 113. So this time we're trying to find V1, the volume of the concentrated solution needed to make a diluted solution. So we get 0.208 liters. I'm going to leave it in liters. Though this is not really a useful value, but it will be for the next step I want you to add to this calculation. So it's 208 milliliters, but again, our solution has a volume of 2.50 liters. All right, next step, let's add to it. It doesn't ask for this in the question. So you would take 208 milliliters, and you would add that to how much water? Remember, anytime you're making a solution from a concentrated acid, do what you oughta, add acid into water. It always goes that way. Add the acid to the water, not the other way around. Especially important with sulfuric acid. The dissolving of sulfuric acid is extremely exothermic. And so if you added water, if you started slowly pouring water into the concentrated acid, that little bit of water would boil, it would splatter, and you'd have a serious problem on your hands. So always acid into water if you're starting with concentrated acid. Now, if you're diluting from 3 molar to 1 molar, 3 molar is not very concentrated. We're talking about taking 18 molar sulfuric acid and making something that is much less concentrated than that. So let's add to this. How much water would you need to add this acid to? Go ahead and do that calculation, please. So the total volume of the solution is 2.50 liters. Of that, we calculated 0.208 liters would be the sulfuric acid. So you'd have to add that to, rounding for sig figs, 2.29 liters of water. All right, last section, solution stoichiometry. Take a look, page 106, 323. Read with me, please. Calculate the volume in liters and milliliters of a 0.324 molar solution of sulfuric acid required to react completely with 2.792 grams of sodium carbonate. So it's just a stoichiometry problem, except instead of giving the amounts of our reactants in grams or moles, we're given some concentration, given a concentration there that ultimately we're going to use to find volume. So sure, we're starting with grams of one reactant, and we're going to use that to find moles of another reactant. So again, we have the molarity of the other reactants. We're trying to find volume. So thinking about the formula for molarity, we need to find moles of H2SO4. So as it shows in the book, converts the grams of sodium carbonate to moles of sodium carbonate using molar mass. Mole ratio to get moles of sulfuric acid. And then again, if you want to do multiple steps, you can, or you can just set it up where you use molarity as a conversion factor. And so it shows in the book there, the very last conversion factor, 1 liter of the solution over 0.324 moles of the solutes. And then that will allow you to find the volume of that solution needed to react with the other reactants. All right, go ahead and pause to number 79, 113. So in this one, given the volume and concentration of a solution, I use those two to find moles. Moles in this case of potassium hydroxide. Apply my mole ratio and then convert to grams of carbon dioxide. You get 1.15 grams. Take a look, 107. Similar problem, except this time we have two solutions that are reacting. We're given the molarity of one solution, the sodium hydroxide, and then we're given the molarity and the volume of the other solution. So again, anytime you're given the volume and molarity of a solution, you can use that to find moles. So find moles of H2SO4 first. Use our mole ratio to find moles of NaOH. And then once we have moles of NaOH, we have the molarity of NaOH. We can use that to find the volume needed for the reaction to occur. All right, 81, page 113. Pause, please. So again, we're going to use molarity as a conversion factor. We end up with an answer of 2.56 liters. All right, that concludes this lesson. Thank you for watching.